a linear bond has a bond angle of 180 degrees, like a line, like a linear line, hence the name. Don't mind the radians, you won't be asked to give any of these bond angle measurements in terms of radians. I am just putting them here because they are better, and degrees are a form of heresy. I wouldn't expect that the exam boards would mark you down for answering in terms of radians instead of degrees, because that would be ridiculous. But then again, that has never stopped them before, so just to be safe, don't do that. Diagonal planar bonds will have bond angles of 120 degrees. Moving on to tetrahedral, which is our first properly 3D shape and is less intuitive than the others. You can't just figure it out, you kind of just have to know this number, unless you're very good at spatial reasoning. And that magic number you need to know is 109.5. Moving on to octahedral, in a shocking twist, the bond angle actually becomes more intuitive. It's 90 degrees. And I mean, just look at it. That being said, remember, these may be shown in molecular formula, structural formula, or skeletal formula, some such kind of thing, so it might not always be completely intuitive. Then there's trigonal pyramidal, trigonal planar's evil twin, with bond angles of both 120 degrees and 90 degrees, like the abomination that it is. You remember that iffy tetrahedral shape, and how you kind of just need to remember the number and it's not intuitive? Well, there are two more of them. If one of the bonding pairs in a tetrahedral structure gets replaced by one lone pair, you get this layout. You'll come across it most in ammonia, and it has a bond angle of 107 degrees. If another bonding pair gets replaced by a lone pair, then you get 104.5 degrees. The most common example of which you'll find is water. And at this point, I can sort of see how my radians method has sort of backfired. Do please tell me if there is something I haven't mentioned, or something that I have mentioned, but not in enough detail. And that's it. Okay, bye.